Hi, everyone. My name is Morgan Chittister, and my project is on Baryon Acoustic Oscillations, or BAOs, and the growth rate from 3D spectroscopic surveys like BOSS and DESI. So I'll give a brief reminder of what BAOs are and their theoretical explanation. Baryon acoustic oscillations are primordial sound waves from the early universe. And these oscillations are explained by linear perturbation theory that we learned in class. So if you remember, in the early universe, there were slight over and under densities. And overdense regions attracted matter through gravity. And photon matter interactions produced a pressure force. And the two battling forces of gravity and pressure resulted in an oscillatory behavior. So I found this animation that kind of shows a depiction of what this would look like with 1D balls. The potential wells are the overdensities and the potential hills are the underdensities. And gravity and pressure are again the forces, perturbing and restoring forces that are causing these oscillations. The bottom animation is showing what these sound waves might look like on a 3D surface. So it kind of looks like a lot of pebbles that were dropped in a pond. The figure on the right is something that we talked about in class, so I'll just briefly go over it, but these are the radial density profiles for dark matter, baryons, photons, and neutrinos. And at the beginning, the baryons and photons are coupled together, so their curve is joined together. And also, I don't know if I said this, but this is like caused from a point-like overdensity at some origin. So as things progressed and when the photons decoupled from the baryons, they are free streaming and the baryons are left stalled here at this characteristic 150 megaparsecs. And basically what happens is as time further goes on, there's no more pressure, but the baryons are going to be attracted through gravity to the dark matter. So they kind of start migrating toward each other. And the result at a redshift of 10 is these two main peaks. And these peaks represent galaxy formation that's favoring near the origin, and then again at this 150 megaparsecs. So a little bit of history. In the 1960s, baryon acoustic oscillations were identified as a potential effect in the cosmic microwave background. And then a few years later, this was extended to the late time matter power spectrum. So if you remember from class, that power spectrum kind of looked like this, where you have P of K on the y-axis and then K on the x-axis, and you had the power thing and then a few wiggles, and those wiggles are corresponding to the BAOs. Then in the 1990s, there was kind of a resurgence of interest in the dynamics of the early universe, and that led to identifying this acoustic scale as a standard ruler for cosmology. Oh, I should probably clear my drawing. 1 second. Clear all drawings. Okay. Yes, okay. So now onto the motivation. Why do we care about BAOs? Well, that characteristic scale proves to be a standard ruler for other measurements. And at high redshifts, you can also constrain the curvature. You can get distance to redshift relations to under 1% precision. And then by comparing the baryon acoustic scale to the physical scale given by the CMB, you can map the expansion history of the universe. And we'll talk about that a little bit later. Also, this sound horizon at various redshifts gives us inferences on angular distance and the Hubble parameter, and that constrains dark energy. So how do we measure the signal? This slide I'll just kind of cover the overview of the BAO method. Perturbation theory and numerical methods, they predict that the acoustic feature is stable to less than 1%. And that's, again, the standard ruler that we're using. So what this method does is it measures cosmic distances against the standard ruler, and then any separations that are found in the line of sight give differences in redshift that relate to the Hubble parameter. And then separations transverse to the line of sight give differences in the angle, which is related to the angular distance. So how do we measure the signal with observational tools? This is where I'll talk about the surveys that are going on. The first survey is BOSS, which is the Baryon Oscillations Spectroscopic Survey. And this survey is part of SDSS3, or the third mapping program of the Sloan Digital Sky Survey. So it utilizes the SDSS telescope. It's a 2.5 meter telescope in New Mexico. And in summary, this BOSS survey should get around 1 million galaxies and cover 8,500 square degrees. And then it'll look at redshift regions between 0.1 and 0.8 and from 2 to 3. Now, this figure up here I thought was really cool to include because this is showing you the evolution of the BOSS sky coverage at different data releases. So this is data release 9, the first column. The middle column is data release 10, and the last column is data release 11. The top panels are projections of the northern hemisphere onto the sky, and the bottom panels are projections of the southern hemisphere. The red colors that you're seeing represent the spectroscopic completeness. So at the earlier data releases, it's not complete in a lot of the regions of the sky, but then in the most recent data release, especially in the northern hemisphere, it's very complete. And this is going to be very promising for fine-tuning precision measurements. So the returns from BOSS, we're hoping 1% precision on the Hubble constant, 0.2% measurements on curvature, constraints on dark energy, matter, and distance measurements. And then constraints on primordial non-Gaussianity. I didn't find a lot of work that I'll be covering in this presentation, but I thought I would include it for those who are interested. And then kind of the overall takeaway is that the BOSS cameras that are used can measure the expansion of the early universe better than we ever have. And just as like kind of a comparison to SDSS, this is the second project, I believe. This is showing a slice of the sky looking at luminous red galaxies. So this left one is SDSS and the right one is from BOSS. And BOSS obviously picked up a lot more red galaxies. So the second observational tool is the Dark Energy Spectroscopic Instrument, or DESI. And this survey is using the MILE 4-meter telescope at the Kitt Peak Observatory. This observatory is in Arizona, fun fact. So this instrument is optimized to measure the subtle imprint of the BAO signal. And we're hoping to measure distance to redshift relations with under 1% precision. And this will, of course, give insight on dark energy. I'm going to just say here that the rest of the presentation, I won't cover anything from DESI because I couldn't find any results. That's not to say they're not there, but the BOSS survey had a lot more readily available work done than DESI. So I wanted to just show an example of how a survey like BOSS can tell us about the growth rate. This figure is taken from Martin White's slides. He's at Berkeley, and he found a figure from Reed et al. 2012. She utilized the data release 9 from the BOSS data. And this figure is showing you a projection of the sky with anisotropies depicted. And the amount of anisotropies is related to the rate of growth. So that's how these surveys can tell us about the growth rate. Some challenges with baryon acoustic oscillations is that they're subject to nonlinear effects. And a way to overcome this was presented in Eisenstein 2007. He showed that these effects might be reversible if you undo the displacements of galaxies with bulk flow. Another challenge is that the anisotropic Fourier space is hard to implement because of the window function. because a lot of the work that was done is assuming an isotropic Fourier space. But the problem with that is that most galaxies aren't isotropic. However, there's been some work done by Boetler 2013 where he didn't place any assumptions on the window function, so it could account for those anisotropies. I didn't list this here, but also Anderson 2014, their work looked at both isotropic and anisotropic spaces. And the Anderson 2014 results, they're like most confident in their anisotropic data. So there is work being done to overcome that. And then last, the BAO method is primarily statistical. You have a weak signal with that has a large scale. So you need a lot of data to accurately report your results. And as we saw, BOSS and DESI, especially BOSS, is accumulating a lot more data, as we saw in that evolution plot, to overcome this challenge. So I'll talk now about the current status of the field. And I first wanted to show how the survey data is matching our theoretical predictions. These figures are taken from Anderson 2014, and I'll just kind of talk about them from left to right. So this is showing you the Hubble diagram, and the solid line is the Planck flat standard model prediction. Planck is just a satellite that is creating this prediction. And then each one of these dots is one of the samples data. So 6DF whatever is one sample, Wiggles is another. And then of course we have our BOSS survey at low redshift and BOSS CMASS is at higher redshifts. At first glance, our survey data matches our prediction pretty well. And then this middle plot actually fine tunes just how well they match in a little bit more detail. So what they did is they divided the Planck, they divided all of the data by the Planck prediction. And so that would equate to unity here when you divide the prediction by itself. Anyway, the dark gray regions are 1 sigma away. And then if you're wondering what this lighter gray curve is, this is the WMAP prediction for the standard model. And WMAP stands for Wilkinson Microwave Anisotropic Probe. Anyway, the takeaway to all of this is that all the survey data it lies really close to within 1 sigma away from these standard model predictions. And then I thought this was cool. In their paper, they were like, okay, what if we compare the survey data to not the standard model? So some of the things they did is they kind of varied the equation of state here, which is the red curve. And then they looked at like a little bit of a different curvature. And again, the takeaway from this is that the survey data matches most closely to our standard model prediction than the other ones. So this next slide is showing you current data for the Hubble parameter. These figures are from Buska et al. 2013, and they nicely compiled all of the recent measurements in a single table. And they have the redshift listed, the Hubble parameter measurements, and the method that was used. And so even though the Hubble parameter measurements, they don't, they obviously don't totally agree with each other, but that's because it's dependent on redshift, right? But the cool thing that they did is because it's dependent on redshift, we can actually look at how these observed measurements at the various redshift look or compare to our predicted standard model within the redshift region that was measured. And so, for instance, Buska et al. 2013, they mapped their observed data, which is this red dot, and then they mapped all of the other observed survey data with all of these other dots. The solid ones just correspond to the BAO method. There were some other methods used, like using supernova as standard candles, things like that. And then this black solid curve is the prediction standard model. So I think we talked about this in class, but from our prediction, we expect the expansion rate to decelerate up until a redshift of 0.8, and then it will accelerate. And this figure just kind of confirms that all of the observed surveys are following that prediction, which is promising. That's good for us. So this slide is kind of the last part of the status of the field I'm going to talk about. But these are some results constraining dark energy, matter density, the Hubble constant, and distance measurements. So the first figure I'll talk about is from Reed et al. 2012, and she used the data release 9 data from the BOSS survey. And basically this figure, what you're looking at, if you just ignore the text in the purple, this is a probability density distribution of dark energy, looking at measurements greater than a redshift of 0.57. And then each one of these curves represents a separate constraint. So like the first is like when they only constrained the growth rate, then they only constrained the angular distance and the Hubble parameter. And then the thing to pay attention to is from those constrained measurements, along with the CMB data, they got a constraint, or so this is the combined constraint on dark energy, this solid curve, and they found it to be 0.74. Some of their other findings in their paper were omega m of 0.28, and then the Hubble constant of 69.3. Some other important results were found in Anderson 2014. So they looked at some distance constraints and Hubble parameter constraints. Now, written, it's kind of confusing to look at, and probably reading the paper will be helpful to fully understand what this is saying in full. But basically, they took their measurement constraints at a redshift of 0.57. Oh, and by the way, they used the BOSS data release 11, so the most recent BOSS data. Anyway, so they have this distance, their uncertainty, and then there's this kind of scale of RD over RD FID. And the reason why this isn't like a solid value is because these values can slightly vary depending on the convention that's used. And so they didn't want to like they have their own convention, but they said that as long as people are consistent, they can find that value themselves. But if you're curious, RD is the drag epoch, which is usually around 150 megaparsecs. And then RD FID depends on the definition that you're using. They used the CAMB definition. This stands for Code of Anisotropic Microwave Background. And that gives a value of 149 megaparsecs. So the same kind of convention is used for the Hubble parameter, but they have these constraints. And then the takeaway from their paper, aside from like the confusing notation, is this DV value. It's boxed here, and then this 1% is saying that this measurement was found within 1% precision. And at the time this paper was written, this was the most precise measurement from a galaxy survey that has ever been done. So it was really exciting. I don't know if I actually said this, but DV is the projection of the sound horizon at the drag epoch. And the equation is written there. A couple years later, Boetler 2016 found a 0.7% distance error on the alpha measurement. And alpha is just a dilation of like a scale factor or something. So in summary, what has my presentation hopefully told you? The Baryon Acoustic Oscillation method has promising results for cosmology. So surveys like BOSS and then others like DESI and a couple others you saw like Wiggles, they're already giving us sub% precision now, and that's hopefully only going to get better in the future. And those measurements are going to help us constrain dark energy, distance scales, the Hubble parameter, things like that, which are important for cosmology. So thank you for listening to my talk. All my references are listed in the slides. And I will just say throughout the presentation, when I reference things, they're like in numbers with little boxes, but Overleaf didn't relate those when it rendered the bibliography. So if you're really wanting to know which reference corresponds, just count the references, and that's how you'll do it. Thanks again for listening to my talk. I hope your projects go well. And thanks for a great semester.